This presentation is going to introduce you to the central limit theorem. So far, we've talked about the normal distribution and the binomial distribution before that. But what we've talked about so far is just one sample. Information that we can gather from one sample, the distribution of one sample, the mean and standard deviation of one sample. Chapter 7 is going to extend that knowledge into taking multiple samples. What if I take many samples over and over again, still within my population, but what patterns start to arise if I do that sampling process over and over again? So we've already talked about population distribution, right? That's that underlying distribution that we're interested in, that large group that we can't go out and sample every single person, because then we just have we'd have census data. So what do we get from a population? What do we take from a population? A sample, okay? And we've been talking about a sample quite a bit in this class. And from the sample, we calculate a mean and standard deviation. Good, okay? And so from that sample, we can get what's called a data distribution. That's what we've been working with all semester. So, right, we can get a sample and the distribution can be bell-shaped. We've talked a lot about bell-shaped data. We can have data that maybe clusters in two areas. So maybe it's bimodal. If you recall from a previous example where we talked about the distribution of digits in your social security number, right? They're all evenly distributed, so they're all equally likely, and the distribution kind of made a rectangle shape, so that uniform distribution. There are many different ways that data can be distributed, and the underlying population could have any distribution, and our sample could also have any type of distribution. We're really going to focus on this bell-shaped distribution that we've already talked about. What I want to talk about in Chapter 7 is, instead of just getting one sample, what if we get many? What if I get, many people to help me go out and talk to 50 different people? So I'll go out and talk to 50 different people, and I'll get an average response, and I'll get a standard deviation of those responses. But what if 10 of us go out and talk to 50 different people? Each researcher that goes out and talks to a group of 50 will come back with their own mean and their own standard deviation, unless we are talking to the same people over and over again, in which case we still only have one sample. But if everybody goes out and talks to a different group of 50 people, they'll all have different means and different standard deviations. So like we see here, this is just a picture representing 10 different samples. So I've got 10 different means and 10 different standard deviations. Well, I wonder, what kind of pattern do those means show? What does a distribution of those means look like? So instead of plotting all of the individual data values, what if I plot just the means? Then that's what's called a sampling distribution. So a sampling distribution is a distribution that's created from taking all possible samples of the same size. So everybody goes out and talks to 50 people. None of this works if one person goes out and talks to 10 people, the other one talks to 25, and another one talks to 50. The sampling distribution has to be created of samples of all the same size. So on your note sheet, question 1 asks you, what statistics can be used to create a sampling distribution? Well, in this class, we're going to focus on the sampling distribution of the means. But besides that, check this out. I've got 10 means, so I can get a sampling distribution of the means, but I also have 10 standard deviations. So I could get a sampling distribution of the standard deviations. Later on in the class, we'll talk about proportions. I can get a sampling distribution of proportions. There's other parameters that we can estimate, that we can compute statistics from samples. In our class, we're going to focus on sampling distributions of the mean and sampling distributions of proportions. Okay, so let's say that we want all groups of 50 in the population. So our population, a few thousand, a few 100,000, and I want to know how many groups of 50 could I possibly get. We'll go back to our counting techniques, and we're going to need to use combination, right? Not permutation, because order doesn't matter. It doesn't matter what order these groups of 50 are in, just as long as they're groups of 50. So we're going to do n choose r, where n is the size of the population and r is the size of each sample. So you have to be careful when we're doing these computations on the calculator, because these numbers get really big really fast. So for example, consider a population of just size 1,000. So that's not even the size of our university. That's a pretty small population. But just to be able to demonstrate the magnitude of these numbers, let's say that we go out and get all possible groups of 50. So that would be 1,000 choose 50. If you put that into your calculator, some versions might give you an error. It might be too much, it can't handle the computations. But it turns out to be this really long number. Who knows what this times 10 to the 84 is at scientific notation? So that means move this decimal point 84 places to the right. So we're going to have, this number, 94606, so on and so forth, with like 75 additional zeros. That's huge. We cannot go out and get that many groups. And that's only for a population of size 1,000. But how many populations are that small? Not very many. So let's consider that infinity. That number's so big, it's reaching infinity. Right? So if we go out, if we could theoretically go out and collect an infinite number of samples of size 50, what patterns would occur? What would happen? Well, they'd all have means and standard deviations, and they'll make up their own distributions. And we're going to look at the distribution of the means.